In this video, we are going to expand our understanding of electric fields in general. We've been talking about induced EMFs due to changing magnetic flux through a coil of wire, and we have not really talked about that in terms of the associated electric field. We've seen induced EMFs that drive currents, that produce magnetic fields, and that leads us to Lenz's law, and the whole thing is, under the auspices of Faraday's law of induction. We haven't talked about the field that's produced by that induced EMF, but any voltage is associated with the field, and so we've got to talk about the field that gets induced by this changing magnetic flux. So let me remind you of something from way earlier in the semester. Integral of E, and this is a definite integral. I'm not putting my units, or I'm not putting my limits here, but they do exist. E dot dl. If you remember, this is a way to determine the voltage at a given point, or at least the functional form of the voltage, given some electric field and some path of integration. In other words, you have an electric field, you're going to integrate that field along this path. You're going to integrate the dot product of this field and whatever path you choose. And that gets you the voltage, which I used to write as a V, but now I'm going to write as an EMF, because what we are talking about is this induced EMF. Remember, this is just a voltage. We just use it to signify certain types. Now, my limits were from some beginning point to some finishing point, some A to B. But what we had said is that the electric field is conservative. So if I take this expression and I just alter it thusly, remember what that symbol means. That's a closed integral. It means my limits are the same point, right? I'm integrating from A around some path and then getting back to point A again, or B, or whatever. And we figured out that because the electric field is a conservative field, that this should give you zero, right? Because that's the definition of a conservative field. Well, the problem here is that in these induced EMFs, I don't get zero because of the changing flux. We have this EMF, which is also equal to minus d phi b dt. Here's the problem. If I induce an EMF because of a changing magnetic flux, that's not zero, unless the change in flux is zero, and then that's a terribly uninteresting problem. But if the change in flux is not zero, I induce an EMF. Well, okay, what happens if I then try to determine the electric field associated with that EMF by integrating around the wire, which would be the logical place to do it? I don't get zero. That's weird, right? So, but I can't get zero because I don't get zero from the changing magnetic, the time derivative of the changing magnetic flux. So what we're faced with is that whatever this electric field is induced, or that arises from the induced EMF, it has to be a different kind of electric field than the fields we've been studying. Now, of course, it's still an electric field, but what we're going to have to recognize is that electrostatic fields, which is what we've been studying, the fields arising from static charges, are conservative. This is what we have known to this point. But now, this is not an electrostatic field, right? This field is arising from this EMF, which is driving a current. This is an electrodynamic field because the charges are moving. Of course, that's what a current is. It's moving charges. So what we now have to say is that electrodynamic fields are not conservative. So the only change I made to the equation that this from earlier in the semester was I made this a closed loop. And for the electrostatic case, that would mean that this was then zero. But this is not the electrostatic case. There are no stationary charges which are giving rise to a field. This field comes from the induced EMF, which drives the current, which is engendered at first by the changing magnetic flux. So I have a different sort of field. This is the first time we've looked at an electrodynamic field. So we have to say that it's not conservative. This equation still holds, of course. If you are interested to know the field, you have this equation at your disposal. This is what we typically focus on, at least in this portion, but we need to understand this new field here. Not really a new field, but it's an old field, but of a different nature. It's now electrodynamic, and we no longer have its conservatism to help us solve problems.